15, here we go. Okay, I'm Nick, sometimes at UAL, sometimes using this thing called Project Cassiel. Half of the printer jam with Evan, so t-shirts available. Oh, they aren't actually, we haven't brought anything with us, have we? But t-shirts orderable. So Evan and I had coffee this morning, and I realized we were actually giving very similar talks because we're solving a lot of the same kind of problems. We're both using web-based pre-visualizers to look at what's going on. Difference is that Evan's working with 3D printers and I'm working with 2-ton metal sculptures. But it's still 3D mathematics, so yeah, this should look quite similar to what you were seeing like half an hour ago. So Cosmoscope, that's the thing. That was on show at Durham there. I've got the stats for it somewhere. So it's 3 meters across, I think, 3 or 4 meters across, weighs 2 tons. Let's see if I can find the stats. Here we go. 3.5 meters, 2 tons, 2,000 RGB LEDs, and it's assembled geometrically. So it's made of a tetrahedra, all kind of stacked together. And it was part of a project with Lumiere and Wellcome Trust. So we're working with scientists involved in researching the very large, so cosmology, the very small, so molecular systems. So that's kind of the visualizations that we were responding to and the kind of experiences we wanted to show on this thing. And there's a photograph of the hardware, and we'll come back to that at some stage. So yes, we're mapping for 3D points to pixels we could use to drive the display hardware, and we'll look at that in a bit. So creative challenge, we can't show video on this thing because it's just not a high resolution screen. You know, you're not going to be able to recognize anything. So no resolution, it's 3D. So what we want to do is use visuals that are driven by code. That kind of makes sense. Code is compact, and if you're writing code, you can work in 3D rather than 2D if you're working in video. And code is transformable. You can combine it in different ways. You can explore it. You can work in maths and geometry. So there's a lot more flexibility there than if you're doing some kind of video processing. And yeah, you can explore it. And it's portable. And I mean a particular thing by that, which you'll see in a couple of minutes. So we built a digital twin of this thing because, you know, digital twins are what everybody's doing. You know, that's fashionable. So this thing is now called digital twin. So it's a previs modeled in ClojureScript, so it's functional Lisp. 3JS based. LEDs positioned algebraically, so I had to do a lot of maths to work out where the LEDs were on the tetrahedral faces of this thing. And the model also creates a little pixel grid that drives the hardware that drives the real thing. And I'll be able to show that when I fire up the live demo of this. So the animation basis. We're working in a vector field. And by the way, none of this is new. I'm sure there's people in this room that have done exactly the same kind of thing when building animations. So we've got our sphere with our x, y, z coordinates, and we have to work out for any point in that sphere, what's the RGB value I want. So RGB is a function of the x, y, and z, normalized to +1, -1. But that just gives us a static visualization. If we want to animate over time, we add a t at the end. So RGB values are functions of where we are inside the sphere and what time it is. The time being, I don't know, a sawtooth wave maybe, or something sinusoidal. Like I say, Evan and I have solved the same kind of problems here for the same kind of reasons. So that's a picture of a previous piece. That's called Plenum. That's King's College, Cambridge. So this is kind of a variant of that. Plenum was just two-dimensional, as you can see. It's just a flat display. And the only output of that was the size of these dots. So kind of like brightness. So it's a scalar field rather than a vector field. So x, y, and z go in, x, y, and time go in, and what comes out is this brightness. And in this one, the points are actually mobile as well, so they were moving around. When I said portable, what I mean there is if you're working in something algebraic, or algorithmic, or mathematical, then if the context changes, like you move from King's College, Cambridge to Torrent in Poland or in Durham, then you can use the same artwork, just change the coordinates, change the density or resolution, and the same code gives you the effect you want. And you can see these things look very different, but also very similar. Same code, different resolutions. No change there. So, generating this stuff, it's all written in ClojureScript, so it's all browser-based. Some low-level code was Emscripten, so written in C and C++ for efficiency, and then that was turned into WebAssembly. A lot of what the visualizations were was they started out being 2D, partly because I had some 2D things in the previous piece, the planning piece, and we had to make those into 3D somehow. So, 2-dimension, function of x and y equals some RGB value. That's great for a flat surface. What you want to do is turn it into a function of x, y, z, so volume and time. And we do that with some higher order stuff. So if I've got a function that can give me a pattern on a flat surface, x and y, I've now got these generators that can take one of those things and make it into a 3D visualization or 3D system. What does that mean? 2D surface, you give it some thickness and you can kind of bevel it so it kind of fades out and it becomes this kind of 2-dimensional slice with thickness. And then with the time you can move it back and forth, rotate, scale, shear, all these kind of matrix operations. So there's a whole bunch of these generating functions that can take simple animations that work in 2D and turn them into more complex animations that work in 3D and vary over time. So we can add thickness to these things. If you only got a 2-dimensional function, then you can't sweep it across LEDs because the intersection will be 0 time. So they've got to have thickness in order for that to work. So we have this kind of beveling effect. And what we get now is what my colleague Mark Downey calls explosive de-abstraction. As far as I'm concerned, he invented that term because I Googled it yesterday and nobody else has ever used that. The idea that if you've got the toolkit, if you've got all these 2D functions for generating these 2D effects, and you've got these generators that can take a 2D function and make it into something that's bent around a shape or mapped onto a sphere or given thickness or rotated, then you can suddenly de-abstract all these things and get huge combinations, numbers of combinations of these things just by bolting them together in different ways. And that's where the explosion comes from. And you've got all the matrix transformations you can do as well. So if you go from 3D to 4D matrices, you can do all the scaling, rotating, all that kind of stuff. And you can do stuff over time. So things move, they rotate, they scale, they fade in and out. So all that kind of stuff. So how am I doing on time? 7 minutes. I might skip that one. So I had one of my examples was, actually, what the hell, let's run it. I can't run it because I'm not online and I haven't got time to sort it. Okay, we'll come back to that or not. Rendering demo, right, let's see if this thing will work. So there's a very simple demo running. It's just a cube, and it's bits of it lighting up as we sweep from one side to the other. And you might think, well, okay, super. That's the sort of thing we give our first-year students as programming exercises. But like I was saying about portability, let's take the cube out and replace it with the actual shape we're interested in. And if my script and code will load properly, yeah, sure it will. There we go. And then we get this thing. The code hasn't changed in terms of the animation. It's doing the same thing, but it's now doing it across this mock-up of our 3D form here. And just to show you the basis of that geometrically, there's our two tetrahedra there. One thing I will show you, I was talking about the hardware and this kind of pixel driving of the hardware earlier. If you look at the very top left there, let's see if I can actually zoom into that. There we go, that thing there. That's the pixel grid that drives the hardware. And we give it an HDMI feed, and what you're seeing there is the signals to drive the LEDs. And it took us 3 days to map all 2,000 LEDs onto the pixels I have on my system. And that itself, I think, is quite a nice little animation there that you can see. Okay, let's see, can I get back out of that? Wrong way, there we go. Okay, so far so good. So that's kind of interesting to watch one of those things for maybe 10 seconds or 30 seconds. But if your piece is running for 4 hours, then it's going to get kind of boring. So how do you make that kind of thing interesting for a longer time period? That's the kind of question that's been answered by musicians working in studios for quite a few decades. If you're doing a music track, you want fade-ins and fade-outs. You want to automate. You want some way of having a set of parameters that change over time as you move along. And as you move back through time, they change back again. So smooth automation, or queuing between scenes. And I'll show you what I mean by a scene in a second. The inspiration for this was something called Audio Mulch, built by Ross Benzina about 10 years ago, which is kind of a Max MSP-like audio system for doing synthesis and performance. And it had effects processors and synthesizers and sample players with knobs and sliders, just like any other kind of instrument system. But it had this thing called the meta surface. So you could take, build a preset with your knobs and sliders, put it somewhere in this two-dimensional space, build another preset, sounding completely different, put it somewhere else in your two-dimensional space, keep doing that so you've got 6 or 8 presets, and you can see the colors here. And then if you move around in 2 dimensions in that space, it morphs or crossfades between all of the parameters for your sound system. So it's kind of collapsing your big state space of all your parameters down to 2 dimensions. So you're losing a lot of accuracy there, or you're losing a lot of space to experiment, but it gives you a very quick way of morphing between completely different setups just by using these 2 parameters. So I thought, yep, I'm going to steal that, good idea. And this is what we have. And if you look at the visualization, we'll see it's right up at the top there. So we've got this 2D plane of these generators, so X, Y, just like Ross's system. You can see them here. They've all got a radius. And we pre-program cues that jump between these things. So we move around in this space. And each preset that we call up goes to a new position in the space in a straight line over a certain amount of time. So you're saying, right, I want you to go from where you are now, wherever that is, to this point, and I want you to do it in 10 seconds. So the cues are X, Y position. Each of these cues, each of these presets has a radius. So the idea is as you hit it and come into the radius, it starts fading in. Some radii are big, some are small. You can see here some of these things overlap, which means you can be in certain points of this state space where you're seeing multiple animations at the same time. And our generating functions now take X and Y in our sphere. They take time, so X, Y, and Z inside our spherical structure, time, and also, what are those, D and H? Distance and heading? Distance and heading. So our animations can respond to how close we are to their preset in our morphing space. And that's used in particular to make sure that the animations fade in and out as we get close and come away from them, so we can get smooth presets between them. And we've got a higher order functor which does that for us, gives us our fading. Yeah, as I said there. So that gives us mixing, so we mix between these things. The system notices if the cursor's outside one of the radii, so it turns off that animator because we don't want to be using up CPU space for that. Ooh, yes, 1 minute 44, thank you. So, okay, quick demo of that. I'll need to live code this. Let's see if I can make that work. We need that. We need that. In there. Right, so you'll see the space here. What I'm going to do is firstly find the correct file. Is it that one? Yeah, down here. I hope this works. So if I can show you the animation there and that. So watch the lights, but also if you can see that pattern there, if I flash this thing here, we get the clapperboard flash, and you might have seen this dot move. If not, I'll give you another one here. Let's go to somewhere else. You'll see the dot is moving very gradually there, and we go through that animation, whatever that is, then through a different animation. Yeah, no, maybe. And then end up with that one. Let me just turn off the house light so you can see that, and turn off the translucency. Example of a higher order thing there. So we've got a two-dimensional animation, 2 copies, 2 different colors, mapped onto spherical surfaces. So if I get the angle right, you'll see there that, in fact, these things are curved as they pass through each other. And then end on, they look kind of pretty as well. Did I have another one of these here? Pendulum. Let's blast that in there as well. And again, this thing Did it move? Did I get it wrong? Did I get my cursor in the wrong place? Who knows? But you get the idea. So yeah, that's it. Thanks very much. Oh, that's the Cosmoscope today. That's what's left of it, rusting somewhere in University of Hertfordshire with all the electronics taken out. Sad days.
Thanks very much, Nick. Do we have a question? Yes, we have a Pattern Club regular. Alan?
Have you tried coordinating sound with this?
Oh, it is a sound piece, yes. If I
Yes.
go back, way back. Yeah, Rob Godman wrote the sound. And essentially the sound score drove my cue changes. He was sending me OSC. And yeah, if you search for Cosmoscope online, you'll find some videos of it. And yeah, it does sound really nice.
We have a question from the back of the room. Okay.
Hi. In the paper that is online for this, there was some mention of some philosophical and scientific concepts around astrophysics and cellular biology and stuff. And I just wondered if you could say something about the relationship between the patterns and the more science-y stuff that's going on. Thanks.
Oh, with my artist hat on, I will say what I was doing was artistic responses to the scientific concepts. Right, and that's the stock answer that everybody says, but that's what it was. You can see some of the animations were periodic, rotations, reflections, some physics modeling in there for the very big stuff, and a lot of kind of pixelated, single pixel stuff for the molecular systems. But yeah, very much, artistic responses to ideas behind the concepts of, and so on.
Do we have one more question? Yes.
Hello. I feel like I've seen similar pixel grids at times from Christmas trees. I was just wondering if you've taken any inspiration from the people that have done that.
Okay, very possible. Yeah, like I say, none of these ideas are new. Christmas tree. I haven't thought of Christmas trees. We didn't do a Christmas animation for it. We should have done. Yeah, one of the tetrahedra could be a Christmas tree.
Yes. I saw Ryman's already selling Christmas decorations, so you can go and check it. Okay, yeah, thanks again, Nick. That was really nice.
Thank you.